cool. Look what we'll have. Secant theta tan theta minus just that integral of the, no, that's plus, right? Secant theta. Aha! So guess what this is? We figured it out. Here's the antiderivative. This plus this all over a 2. Put that over 2. Or you can put a 1/2 in front of this whole thing. Cool though. It took, when I like these hard problems, it took a while, but we got that antiderivative. You know what this is? Do you recall that from before? That was a natural log. Natural log of secant theta plus tangent theta. You can go back to your notes when we actually derived that one. So this is now secant theta tan theta all over 2 plus 1/2 of the natural log of secant theta plus tan theta. And we're just going to plug in that 0 and 2, right? The only thing is, these were x values, true? These were x's. You go, how do I get the x's back right here? Tan inverse. Yeah. We'll put it all right in there. So thanks for being patient with me. I just wanted to see, sometimes in math, this was a good experience. You might keep going somewhere, like, it feels like you're getting lost. And you try integration by parts, and it looks like it got worse. But in fact, it got really nice. Because this emerged again. And we're thinking this was over here, and we're able to just say, hey, well, 2 of these equal that. So divide by 2. So there's the antiderivative right here. I'm just going to resubstitute everyone, and then plug in an x equals 0 and x equals 0. Okay, so let's see. I need this. And what do we get now? What's secant theta? You can use that triangle. What's secant theta? Square root of 1 plus x squared. What's tan theta? Times x all over 2 plus 1/2 natural log of, what's in the bars? Secant of theta is square root of 1 plus x squared plus x. And where are we going from? 2. Isn't that cool? Got it.
Where'd the ln come from?
The natural log came from this integral of secant theta. Just because that would have taken a few more steps to go through that again. That's the problem where to do that integral. If you're curious, to do the integral of secant theta, you got to multiply that secant theta plus tangent theta over a secant theta plus tangent theta. I'll just go like that, because that's 1, right? Distribute that, and then you do a u sub that works.
Thank you.
You're welcome. So, and that's where that one came from. But you can call, we did that earlier, the integral of secant theta. Turns into that. So when this is where this, you was wondering where that integral would come from. You get ln of secant theta plus tan theta plus short theta. Hey, I'm going to put these numbers in. All right, what's 2 squared plus 1? Square 5. And when I'll put that 2 in front, all over 2. Plus 1/2 natural log of, what's the square root of 5 plus 2? It's positive, so I'll just write square root of 5 plus 2. And now what do I got to put in there? Push that's over 2. You can cancel these 2's, right? Don't agree? That was that x value 2. So you just knock these out. Now I got to put in what? Subtract, and then put a 0 in here. Oh, a 0, I like zeros. You put 0 here, what's it turn into? 0. You put a 0 there, you get the natural log of 1 plus 0. What's the natural log of 1? 0. So when I'm just going to put minus 0. If you put 0 in that whole thing, you get 0 again. That's the answer. That's the length of the arc. But what's cool about it, this is exact. I'm not going to put the minus 0 because minus 0, we don't need that, right? This is the exact length. So if you check Wolfram Alpha, use a TI-89, a TI-Inspire, something that has a computer algebra system, a CAS, you get this. And what's neat, sometimes people, I wonder how that came about, just by that method we just did. Now, of course, regarding tests, students get a little fearful of a problem like that. You know, which one was a little bit easier? The first one? Right. So this one, I'll be honest, the wording in the book didn't have that word there. So this was what? Exact. So in this problem, everyone, in number 19, all they said was, ready, I'm going to read this to you, find the length of the arc. So if they say that, then they're not saying it had to be what? Exact. And if you're allowed your TI-84 83 calculator, you agree you could have done this problem without doing all that you know, you could have just done what? When we had it set up at the beginning, what was the beginning part? It wouldn't have been quicker? From right there, do it via what? Calculator, true? Definitely. So I just want to point that out before you get all, because I know that problem can be intimidating. You're like, man, that's 3-4 pieces of paper get that thing. But it is cool. I thank you for being patient with that. So this problem we didn't have the word exact, but I knew you all good enough to get the exact line. So great job. Hey, before we do 8-2, let's come up with something with this. Let's write this another way. Can I write? Cool. Plus, when you see something like that, it just makes you more powerful in math. If you see that again, you're like, ooh, I have to attack a problem, and you get that integral to reemerge again. You just add it to the other side, like Kate, you suggested. That's the way you can find that antiderivative. That sometimes happens in integration by parts on the more complicated problems. I'm going to rewrite that. This kind of leads into the next section, 8.2. I'm going to call this, this is going to be arc length. S of x. S is a function of x. Let's just say this is arc length. That's an S, not a 5. Make sure it don't look like a 5 here. S. And it equals the integral from a to b, square root of 1 plus dy over dx squared dx, right? Well, I'm just curious. By the fundamental theorem in calculus, what would this be? Just something we can do to lead us into the next section. What would ds over dx be equal to? What happens? I can just remove the what? Yeah, take that integral off. What are you? Square root of 1 plus a dy over dx. So isolate the ds. What would ds equal? They call this the differential. The differential. What would ds equal? 1 plus dy over dx squared, and put the dx what, right over here? Will that work? I'll make sure this hat goes all over this. Make that bigger. There you go. So we're going to think of, from here on out, how about ds is equal to, it's called a differential, is equal to square root of 1 plus dy over dx squared dx. Right? Outside angle. And it makes it easy to write some of our next upcoming formulas in section 8.2. I just want to show you how we can write ds. I'm going to put or. What else could ds equal? Or ds could equal, what would it be in terms of the other one? Yeah, dx dy squared times that. Now I'll leave that up here. So I'm going to erase this part right here. And I'll make this 8.2. And this is surface area of revolution. And I'll write those up there to kind of get it going with the next section. Well, good, Connor.
What's the differential solved for?
The differential?
Is it still the arc?
Say again, I'm sorry.
Like, what does the differential give you?
You know what? I'll draw this in a picture. I know it's funny, it's like, what is a differential? We always think of ds, dx, dy, dx. I'll draw a picture to help you see this.
Okay.
And I'll tell you where I'm stealing this image if you're curious. It's on page, hold up. Like if you had your book with you, if anybody had it, buddy, go look at a nice picture. It's on page 542. But I'm going to draw it for you. Like, he's like, what does that look like geometrically in terms of a drawing? But this leads into this next section. I'm going to put it down. Area of surface revolution. All right. of a surface of revolution. These were arc length formulas. I can leave that up here. What was S equal to? You know, S of X, arc length. That was equal to the square root of, from A to B, 1 plus dy over dx squared dx. But now I'm going to write these. Dx equals 1 plus dy over dx squared dx, or we could say ds equals the square root of 1 plus dx over dy squared. So in contrasting the question, I'm just going to draw a triangle. Let's go from a point here to a point here. I'm just going to draw a triangle here. You'll see this image, everyone. Don't want to make that too steep. That'll work. That's a tangent line to a curve at this point. Alright, so go like this. I'll go here. Now I'm just going to make a triangle here. This is from one x point, and it's a tangent line to the curve there, Connor. We can call this a change in x values. So I'll just write dx, which is change in x. The dy goes from here to here. That's the differential dy, that's also a differential. So from here to here is dy. And you see that right triangle there? From here, this point, I'll take that off, is ds. That's that differential. And do you see Pythagorean theorem? I'm going to write it out. What's dx squared plus dy squared? Yes. But you want to actually see what it would look like in terms of that differential. The reason we're doing this, the whole reason behind this, Connor, is to make the next section's formula, 8.2, just easy to remember.
Okay.
That's all we want. We want to say, I'm going to forget all these, I'm going to memorize this stuff. Heck, you might find this helpful. And when we talk about mnemonic devices in this course, like what? What's a mnemonic device to remember where trig functions are positive? All students take what? Calculus, all students take RAG. And we got a mnemonic device to remember the 5 Great Lakes. Someone has one, right? Oh, I thought someone knew it. No one got one? Holmes? Holmes, you know that? I know this isn't, I'm not studying Great Lakes in here, but what's Huron, what's that? Ontario, Michigan, Erie, Superior, I mean, we're talking about mnemonic devices, right? This right here is a mnemonic device. What would ds equal? Right there, just that picture, and this is the Pythagorean theorem, we all know that. What would ds equal? Just that square root of this. So I'm going to do that. And so this right here is just a mnemonic device. Connor, anybody here, feel free to use this to help you remember this. Because if you're like, I might forget this. If you know this, everyone knows Pythagorean theorem. ds would equal the square root of this. What if I factored out a dx squared? And I took that out of there. What would you have? You ready? I'm going to factor it out of here. So what's the square root of dx squared? dx, but then this would just be a what? 1, but then I have to have a dx here, so this would be a dy squared over dx squared. Did everyone see that? You see what I did? I just factored out a dx out of this expression. Or dx squared here, and that's an easy way to remember it. Or what's another way I could have factored out the what? So Kate, it's just another way, or anybody in here, just a mnemonic device to help you remember what this ds is. In terms of that differential. Someone see what I'm doing? I'm just saying, well, you can factor out a dy squared. Yeah, but then you'd have to do dx over dy. Isn't that cool? So that's just a mnemonic device to help you remember. Similarly, factor out a dy, you'd have what? Dx over dy squared plus a 1. Isn't that cool? But I don't know. That's up to you if you're like, that doesn't help me. Right? You might find it easier. We derived that formula earlier. You might find that easier.
Should that be a dy?
Ooh, right? Where's that dy be? Yeah, you're the best. That should be a dy. Thanks for spotting that. I appreciate that. So this one is going to be the dx. This one will be a dy. And Isaac, I think I'll show right now what you're talking about, why that's going to be the case. Because right here, if you factored out a what? A dy, what would be left over? This would be
Dx, dy.
dx over a dy squared. And this turned into the what? 1. There's why that's got to be a dy there. So ds can equal either of these. So now, what are we doing in section 8.2? Area of a surface of revolution. Okay, well, let's draw a couple images here. Let's think, all right, we got some image like this, and we're going to revolve this around about the x-axis. We won't do the entire math proof, it is in the book, but we can at least get an idea of what would be the formula. So we got to revolve this around this curve right here. We got to revolve that curve from there to there about the x-axis. Let's just think of one disk right here. Like that. And that gets revolved about the x-axis. So if this curve got revolved about the x-axis, we had to get the surface area of this thing. Here, I'll make another one. Let me stop there. All right. We just look at that one portion getting rotated around. This is the y-axis, right? Isn't that just distance y? This is just distance y. From there to there. Now this is just some function, what, right here? Y equal to what? F of x? Some function y equals f of x. But the distance from here to here would be y. What would be the circumference of that circle right there? That would get formed if it got revolved about the x-axis. 2 pi r, right? Is that circumference of a circle? 2 pi radius. So think about it, everyone. If you had to get the surface area of a cylinder, well, a cylinder is just a nice perfect shape like this. When you get the surface area of the cylinder, it would be 2 pi r times the what? The height? The only thing is with these curves, it's not straight, is it? It's not flat. But we can use this, right? To think of that length. It would be 2 pi r times that what? That length. And that's what's coming out of here. So what we're saying is, this would give us the surface area. You want to write SA for surface area? Unless you want to put a big S. I already got that little s over there. See that little s for arc line? So I'm going to use a capital S, capital A for surface area. What would be the formula here? It would just be 2 pi times the radius. Look at the image. What's the radius? A y or an x? Look carefully at it. The radius is the letter y. I like the color good, so I'll put that y. And then I'm thinking, well, that would just give me that circumference. Now we've got to think of summing up an infinite amount of circumferences along that curve there. So that's where I need this arc length thing. Well, I'll just put ds then. So this is an easy way to remember the formula. And I'll keep this up all class. I may push it over there so we have some room to write. There you go. Now let's make one more formula. And that's the formula. How about 2 times pi times y, where y is the function f of x. And then ds. And you go, what's ds? This right here. Or this. You might say, well, which one do I use? It depends. It's up to you. Some problems you can use either or. If you want to keep everything in x's, great. If you want to get everything in terms of y, use this, true? Isn't that awesome? Hey, but we do have to do one more. What if it got revolved about the y-axis? That formula should be very similar. I bet you a lot of you already know. But let's draw it so we can really look at this. Images help us see something. Now let's just say you got this, you got some curve like that. And you got to revolve that curve around the y-axis. So it would look like what? Yeah, so this would reflect here. From up here, and everyone, I'm just gonna draw one circle here. There's the radius, and then here's one circle. Going all the way around. Well, what's that distance from there to there? That's not y, that distance is what? That's x. So the radius now will be x. And so what would give us the surface area when some curve gets revolved about the y-axis?
Be 2 pi x ds.
You got it? Excellent. This would be surface area. Hit the curve. They revolve about the x-axis. Surface area. Hit the curve. They revolve about the y-axis. SA surface area, or just capital S, would equal 2 pi times the radius x 2 pi r, and then I'm like, not just one of these, I need an infinite amount of these, a limit, because that approaches infinity of these, and I'm thinking along that arc length right there. ds? Just keep in mind that ds is really this, right? But it's your choice, which one you want to use. I think it'll be obvious that when you're working a problem, that everything's in terms of actually pragmatic exacts. What's neat though, if you ever want to try a problem both ways, it's neat to see it both ways, so you see it works either way when you set it up. Cool. Just make sure, if you've got dx in your integral, doesn't everything have to be in terms of x? Yeah. If you've got a dy, then make sure everything has that variable y in there. Alright, so let's transform these. What's the surface area? About the x-axis. What's the formula? Surface area equals 2 pi, I forget the letter.
Y.
So when I forget, you guys are great. I just draw a picture to help me remember. Seriously. I'm like, is it y or is it x? I'll just draw a quick picture to see, well, what would be the radius if I went around the x-axis? And what would be that radius? That one radius would be a distance y. Don't see how that's the distance y? You can just draw. Sometimes, all you have to do for your memory, and we were talking about mnemonic devices earlier, but pictures help. For our memory, sometimes you just have to draw one little circle to help you, oh yeah, that's the one. And then this ds will be, one of these. And what's the surface area? About the y-axis. 2 pi. Obviously it's going to be x. And I like to put little images to help us see that. Let's just go like that. Go like that. This is the curve. That distance right there for that one circle would have a distance x for the radius. Cool. Just an easy way to remember it. I'm serious, like 3 years from now you can remember that. You're like, surface area. Well, I know arc length. Arc length being, in terms of the integral of this, we can just call this portion ds, and we're good. All right, let's try one. Now that we got this thing set up. Oh, this is in section 8.2. I think it's always good, we do a couple of these. Oh, they put the word exact again. Let me put it. Find the exact. Find the exact area of the surface obtained by rotating the curve about the, in this problem they said the x-axis. And I'll give you the curve. What's neat about this, and we'll set up the problem, just because it's about the x-axis. I didn't want you to think mistakenly that you're forced to use that. Remember, the beauty is ds can equal either one of these. But you might find it easy just to do it that way. All right, what's the curve? Okay, y equals x cubed. And x goes from 0 to 3. Hey, you want to draw a small image of this and help us figure out what that radius is again? Small picture. What's y equals x cubed look like? It's like that, right? Is that y equals x cubed? It starts getting high though. What's 1 x equal to 3? 3 cubed is what? 27. So it really gets pretty high there, but we're going around which axis? About the x-axis, so I'll just reflect this. Like this. Funny looking thing. I'm just going to draw that one circle right here. There's the radius. And that's the distance y. So it would be the surface area. Radius y, surface area would equal 2 pi. You put the 2 pi out front, right? What's the radius? Y. Yes. Two pi radius times that arc length. Now, I'm going to use this one. Here's my reason why. They gave me limits for x, right? I just thought they'd give me the values for x there. I thought, I'll approach the problem that way. It shouldn't be too hard. If it becomes a problem, maybe I'll change the dy. 2 pi, I got to get everything in terms of x's. So what's the limits? 0 to 3. So what do I have to substitute for this letter y?
X cubed.
Excellent. I want to make sure everyone sees this. Did you hear he says you're going to put x cubed in? If I'm going to make everything the dx, there's my limits in terms of x's. Well, then I can't leave out a letter y. I have to substitute whatever y is. Y is equal to x cubed. Now I'm going to put the ds, which is the square root of 1 plus derivative of y with respect to x squared and a dx. That's the ds right there. There's that ds from that differential. But what is the derivative of y with respect to x? So I'll find that dy dx. Bless you. I don't know why I get that a lot on tests. I don't know what that's about. It's not that. What is this?
3x.
3x squared. I don't know what. Sometimes I get 2x squared, 3x. Yeah, it's 3x squared. So let's put that in there. And what do we have? 2 pi 0 to 3x cubed. 1 plus, I need you to square 3x squared.
So 9x to the 4th.
So square the 9, square the x squared, 9x to the. Let me make sure people are okay. The setup's the hardest part. I know you can do this integral. That's a u sub, isn't it?
U.
That's just a u sub. I know they said exact, but we're just going to do a u sub here. Is that okay with this? So this will actually get us the surface area right here of this image. Y equals x cubed, getting revolved about the x-axis, go all the way out to x equals 3. Okay. Kate?
So what's the difference between using a U sub and using the triangles?
And using the triangles, you know, because triangles involve substitutions. We just say u sub that we're just not even going to do any trigonometric substitution, if that helps. So when I say that we're going to do a u sub here, but I follow you, you saw this square root. I got to trying to figure out what she's talking about, and she noticed the radical, which often occurred in the trig substitution. But that takes a lot of work when we do those, don't they? They take forever. But do you see the power difference? This was, I was like, oh, this is just going to be a simple let u equal something, no trigonometric functions needed. If this power in here is higher than this power out here by 1, it always works. I would have had trouble though if this was like equal to this, or if this power was less than that, which sometimes happens. And you go, where are you going with that? You know, that you might even get to a problem where it's like, oh, I need one of those trig formulas that we did earlier in this course. It's a great question, because I got you. It did look like a trig substitution. I don't know what this. We see radicals, we're like, uh-oh. That trig substitution? All right, something like u equal to 1 plus the 9 x to the 4th. I'm trying to knock that x cubed out. What's du?
36 x cubed dx.
Yeah, Armando, thank you. And then I'll isolate the x cubed dx. So we can substitute. 136 du equals x cubed dx. Bye-bye. And bye-bye. If I substitute that. And I won't forget about my 2 pi, right? 2 pi. Integral. 136, might as well put that out with the 2 pi, right? Heck, might as well put it underneath the 2 pi. And just the square root of a u. Love it. Not gonna be bad at all. Do you wanna change the limits? Let's do it. What's 1 plus 9 times 0 to the 4th? 1. Feel free to pull out a calculator. It's gonna get big. What's 3 to the 4th times 9 add a 1?
730.
730. Everyone see that? This is when it got gigantic. It's the idea, oh yeah. Because how high this thing was getting this 730. That's 3 to the 4th, 81. 81 times 9. What she was saying is 729 add to 1, 730. So that's a 730 to a 1, the integral of square root of u. What's the integral of square root of u? 2 pi over 36. 2/3 u to the 3/2, and you're going from 1 to 730. Again, if you don't like to use u's, just resubstitute x's and put those x values at 0 and 3 in there. How about these 2 over 36 and another 2?
It goes to pi over 27.
Thank you. Pi over 27, everyone. 2 times 2 is 4. 4 over 36 is 1/9. And 9 times 3 is 27. Outstanding. And here we go again, everyone. Here we go again. 730 to the 3/2 power is irrational. When I write this answer, here's my surface area. It may look funny. 730 raised to the 3/2. Subtraction of 1 to the 3/2. What's 1 to the 3/2? This is fine. Nice. Write it like that on an exam. That's great. How does Bob write it? 730.